Hello, welcome back. This is Calculus by Dr. Oz. Today we have an exercise where we're going to determine convergence or divergence of the given series. So we're going to check if the given series is a known series like geometric series or telescoping series. If the given series is one of those series, then we have a specific way to handle handle the convergency of those series. If not, we also have the Nth Term Test to prove the divergency of the test. So we will check if there's any infinite series in the list that we can use the Nth Term Test for. So we have 3 of those series. This could be a relatively longer question. So let's get started. Right, let's start with the first infinite series, and that is 1 over n minus 1 over n plus 2. This looks to be like a telescoping series, but we have to write the terms in the partial sum carefully. So let's start. All right, here we go. I'm going to write S sub capital N, starting from n equals 1. So n equals 1, we have 1 over 1 minus 1 over negative 1. This should be plus, by the way. I think there's a typo. Yeah, that's a plus. Okay, and so that should be 3. Okay, plus for n, this is n equals 1. For n equals 2, this is 1 over 2 minus 1 over 4. Let's write also n equals 3, 1 over 3 minus 1 over 5. Maybe one more, because it's better to explicitly write down at least the first 3-4 terms and the last 3-4 terms. So 1 over 4 minus 1 over 6 plus plus. So now I'm going to write the n minus 4th term. So 1 over n minus 4 minus 1 over n minus 2. Okay, n minus 4th plus n minus 3rd, 1 over n minus 3, n minus 1, okay, plus n minus 2nd, okay, plus n minus 1st, and finally the nth, okay. So 1 over n minus 1, 1 over n plus 1 plus 1 over n minus 1 over n plus 2. All right, I think we have the full picture now. So now let's see which one cancels which. First off, here 1/3 cancels this 1/3 here, okay, and 1/4 cancels this 1/4. So as you see, like there's nothing to cancel 1/2 and 1. Okay, probably 1/5 is going to be canceled by another term here, which we don't have, and then 1/6 as well. So let's see, let's look at the last 4 terms and what cancels. So here 1 over n, 1 over n minus 2 is going to cancel this 1 over n minus 2. 1 over n minus 1 is going to cancel this 1 over n minus 1. Okay, and 1 over n is going to cancel this 1 over n. And there's nothing to cancel this and that, and you can check by yourself that these 2 terms are also canceled by the 2 terms before the n minus 4th terms. So in this particular case of telescoping series, we have 2 terms in the beginning and then 2 terms in the last surviving. So I can go ahead and then say that Sn is equal to 1 plus 1/2 minus 1 over n plus 1 minus 1 over n plus 2. Okay, after having all the cancellations. All right, so we know that the limit of the partial sum as capital N approaches infinity, that's what we mean by that, is equal to the value of the infinite sum. And what was the infinite sum? That's 1 over n minus 1 over n minus 2. So let's see what this limit is. Okay, Well, as n approaches infinity, this term and this term will approach 0, and only these two terms are going to survive. So the limit value is going to be 1 plus 1/2, which is in fact 3/2. So I can go ahead and just say that this infinite series is equal to, or infinite sum of numbers is equal to 3/2. Okay, so again, we use the telescoping series, but you're going to be very careful of writing the terms in the sum explicitly, and maybe for the first 4 terms from the beginning and for the last terms in the end, to see the full picture and to see like what cancels what. Okay, and then we deduce that the sum is convergent and it converges to 3/2. All right, so going back here, this sum is in fact 3/2. Okay. So let's look at part B. Part B is the infinite series of ln 1 over n. So again, there is no test or there is no aid provided to us, so we have to sort of like guess what kind of like test, what kind of strategy we're going to apply to prove convergence or divergence. So ln 1 over n can be written by using the ln properties that we know from pre-calculus. It's ln 1 minus ln n, okay? And ln 1 is just simply equal to 0. Okay, again, this is pre-calculus. So what that means is this ln 1 over n is equal to minus ln n. So I can rewrite this sum as, I can pull the minus out, ln n, okay? So this looks to me that this is a divergent series because the nth term does not go to 0, and I can prove that. And at the end, I can use the nth term test to prove the divergency of this infinite series. So let's look at the limit of the nth term, which is minus ln n, right? Or you don't need to put minus sign, but this limit is in fact minus infinity, or in other words, it just doesn't exist. Okay, so well, either way, you have this limit not equal to 0 by the nth term test. Nth term test, right? I can conclude that this is divergent. Remember that we use the nth term test to prove divergency, not convergency. All right, so this is a divergent series, okay? And finally, so I can write here that this is divergent as well. Okay. Finally, we have the infinite series e to the minus n. All right, this looks to me like a geometric series, as I said, and if you just list down the terms in the sum, for n equals 1, it's e to the minus 1, e to the minus 2, e to the minus 3, on and on and on. So this sum doesn't start from 1. So to make it look like a geometric series, we must have the sum starting from 1. So what I'm going to do is cheating a little bit. So I'm going to add 1 to this sum, okay? So this is going to be an infinite sum, but eventually I'm going to subtract 1. How about that? So this way I can rewrite this sum as a sum starting from 0, okay? But once I have the sum, then I have to subtract 1 from the sum of the geometric series. And why is it a geometric series? Because this is the general term is just, you can write the reciprocal of that. It's e to the 1 over e to the n. It's in fact 1 over e to the power of n. Okay, so here, the good news is that a is 1 and r equals 1 over e because we have the exact same form of a geometric series here. Okay. So this tells me that, let me just continue from here, that this sum is a over 1 minus r, but as well I have to subtract 1 from the sum. And again, I'm using the geometric series properties here to represent this sum by a over, all right, 1 minus r. Okay. So let's simplify this, but I have to sort of like clean this up a little bit. Okay, let me just clean this real quick, and you will see that the bottom, if you write this as like e over e, so you have e minus 1 over e minus 1. Okay, let's flip this over, e over e minus 1 minus 1. Okay. And then this is equal to e over e minus 1 minus e minus 1 over e minus 1. Okay. That takes you all the way to 1 over e minus 1. We can just simplify this to get 1 over e minus 1. All right. And here I'm showing that in part A, the telescoping series converge. So this is sort of like an animated version of that, and the convergent rate is pretty not bad. It's slowly converging to the limit value, the value of the sum, but still it's not bad. And this is the series in part B. We said that the infinite series is divergent. As you see, like you are going down, so the values get smaller and smaller without a bound. So you're diverging away to minus infinity. Okay, so this is sort of like the visual proof of what we concluded in part B. And this is the graphical output of the last example, for which we had the geometric series. As you see that the convergence is pretty rapid, and we converge all the way to the sum. Partial sums converge to the actual sum pretty rapid. All right, I think that explains the whole exercise. Thanks for watching. I'll see you in another video.